So for this problem, we're asked to solve the beam structure using two elements and work equivalent loading. So we can we're given that the moment of inertia, elastic modulus, and the section modulus are all constant across the whole section. So that's very convenient. We have two distributed loads. A distributed load that acts along element 1, which is equal to 20 pounds per inch. And then we have another distributed load, Q2, which acts has a distributed load of 10 pounds per inch. Okay, and we have two beam elements. We have one beam element that is 12 inches long, element 1. Another beam element that's 24 inches long, which is element 2. So we have a concentrated force of 200 pounds acting at node 2. And then we have some unknown forces. So at node 1, we know that because a pin joint, we know that the displacement at node 1 must be equal to 0. At node 3, we know the displacement must be equal to 0. And then we have some reaction forces. So we have a reaction force at node 1 we don't know. And the reaction force at node 3 is unknown. So the external force applied at node 3 and, sorry, not 0, it should be 0, is unknown. Right? So first thing we're going to do is we're going to define our elemental stiffness matrix for element 1 and for element 2. Right? So for element 1, this term out in front is just equal to elastic modulus of the beam times the moment of inertia of the beam divided by the length of the beam cubed, or length of the element cubed. All right, then everything in this matrix here, I'm going to highlight in underline in green. This is just the length. All right, everything else. All right, so these are all things that are just given to you. Okay, so all you have to do is just calculate it. And if you end up calculating it, you end up with this matrix here. All right, and we can repeat the process for the second matrix here, where we have E is the same, I is the same. Now the only thing that's changed is the length is doubled. So the length of element 2 is 24 inches. So let's plug that in to our equation here, and we end up solving for the stiffness matrix for K2. Right. Notice we've factored out a common coefficient here. And then we have a 2-element problem where we have shared nodes. Our shared node is node 2. All right. So we look at the rows and columns that have those shared nodes, a shared degree of freedom, V2 and theta 2. And we're going to combine. So what we're going to do in a second is we're going to combine those common sections. Okay, so we end up with our elemental equations here. This is for element 1, and this is for element 2. So the only thing that we had to add here is this term here is equal to that term is equal to Q1 length 1 over 2. I'm sorry, this is element 2. This is element 2. This is element 1. All right, this should be this should be equal to Q2 length 2 over 2. All right, and then this would be, for this value here, would be equal to Q2 length 2 squared over 12. All right, and then these terms are the same, and these terms are the same. All right, and then for element 1, this term would be equal to Q1 L1 over 2, and then the second term here would be equal to Q2 L2 over L2, sorry, Q1 L1 squared over 12. Right? So that's just from our definition. So for a distributed load, we have to account for those the equivalent concentrated forces and moments at the boundaries. So so if we do that, we can now assemble our global stiffness matrix using our shared using the shared nodes. So we have our shared nodes are going to be highlighted in yellow here. Okay, these are the ones that correspond with V2 theta 2 here. Right. So now we have our global stiffness matrix. We can then use our global stiffness matrix to define our, I guess the other thing I should point out here is that to define our system of equations here. So notice, the one thing I like to note out here is that we have to include all of our unknown, all of our nodes due to all of our forces due to our distributed loads. So those are the forces we had defined these elements here. There's two elements, V2 and M2, and we had to add them together. So we had to add them together. We got minus 240 and negative 240. So that's where this minus 40 and negative 240 come from here. Okay. So the next thing is we can't solve for the first row equation because we have an unknown term here, and we can't solve the fifth row equation because we have an unknown term here. So we're going to get rid of those two. Okay. We're also going to apply our boundary conditions of our problem, which is V1 and V3 are equal to 0. So since V1 it would correspond with the first column, and V3 would correspond with the fifth column, what remains here is these terms, which will give us a 4x4 matrix. Okay, so which is our reduced matrix here. All right, so this is our applied forces that have been reduced. This is our global stiffness matrix that's reduced, and this is our known nodal our known displacements. Right? So we can then take our inverse of K reduced, and we can solve for theta 1, V2, theta 2, and theta 3. All right. So so if we do that, we'll end up getting these values for theta 1, V2, theta 2, and theta 3. All right. So if we go back to our original system of equations, we can then solve for R1 of y and R3 of y. So if we go take our original equation on the top of the page here, and we look at the first and fifth rows, we end up getting these algebraic equations for R1 of y and R3 of y. So if you plug in all of our theta 1, V2, and theta 2, which we know now, we can then solve for R1 of y and R3 of y. So the next step we have is we can then calculate our nodal forces and moments. So we have, if we go back to our last page, we have these two equations for element 1 and for element 2. So using these, we can calculate our nodal forces, which we have on the left-hand side here, M1, V1, V2, M2 for both element 1 and for element 2. So we know everything on the right-hand side of the equation now. We just need to calculate the nodal forces and moments. So if we do that using these two elements, using these two equations here, should be able to calculate our forces and moments, which are shown here. Okay. And then we can take a section cut of our system at a point, and we can calculate mz of x as a function of x. And what we end up getting is that the maximum, because we have a distributed load, our maximum bending stress is unlikely to occur at our nodes. So we need to make sure that we account for it. So what we end up getting is our bending stress as a function of x is going to be equal to our maximum is equal to 537.8 for our first element, and for our second element is going to be equal to 889. All right, so we can just take a section cut as a function of x. We can solve for our the moment at the section cut. So as long as we do that, we can end up getting these different graphs, and we can then, using our maximum moments within each of our elements and the section, the value of the for the section, which is just equal to S1 is just equal to I1 over C1. So that was given to us, so we can then solve for stress, maximum stress within each element. So maximum stress occurs in element 2, and it has a value of 5.93 kpsi. So that concludes this lecture on finite elements beam theory, using beam theory. Using beam lengths. So the general process is the same for both cases of distributed loading and concentrated forces. But over, so for the main thing of these problems is just that they take a little bit of time. They almost immediately require that once you get into, especially with beam elements, that it's very beneficial to use software to do your inverses and your other things. So just make sure as you're going along, have your calculator nearby, check your work as you're going along, and you should be